The next page just takes us through some more additional examples. R equals 3 secant theta. We're going to do our test for all three of them. Now, secant we know is the same thing as 1 over cosine. And we know that cosine has a polar axis reflection. So my first gut instinct is that it's going to have polar axis, and I'm not sure about the others. So as I do my math here, we'll first start with polar axis. For every r theta, we're going to plug in r negative theta. So r equals 3 secant theta, plug in a negative in place of theta, so 3 secant negative theta. And secant is an even function, which means that when I apply my even and odd identities, the negative sign goes away. So I end up with just my original, again, 3 secant theta. These two things are equivalent. So I can say, yes, I definitely do have polar axis symmetry. Theta equals pi over 2. For every r theta, negative r negative theta needs to be on the graph. So we'll substitute in wherever we have an r with a negative r, and wherever we have a theta, a negative theta. So r equals 3 secant theta. Negative r equals 3 secant negative theta. We'll then apply our even or odd identity here. Secant, once again, is even, so the negative sign goes away. Then we divide through by the negative 1 to get r by itself. And comparing 3 secant theta to negative 3 secant theta, those are not the same. That is a reflection, so they're going to look like two different graphs. So there's no theta equals pi over 2 symmetry with this graph. Then finally, the pole, for every r theta, negative r theta needs to be on it. So r equals 3 secant theta. If we plug in a negative over here, then divide through, we're obviously not going to have the same. So we can say most likely that there's no pole symmetry. Once again, we can say it looks like there isn't. We can't rule it out completely until we confirm it with the graph, but this graph does not have those types of symmetry. Okay. Looking at example 3, r equals 4 over 3 minus 2 sine theta. Once again, I see a sign in there, so my gut instinct is to say I'm going to have theta equals pi over 2 symmetry, since that's what our r equals sine of theta graph has. So first of all, if we go for every r theta to r negative theta, if I plug in a negative theta and then apply my even and odd identities, 4 over 3 plus 2 sine of theta is not the same as 4 over 3 minus 2 sine theta. So it's not the same as the original. The second one, though, gets a little bit more complex because we have to divide through by a negative. So here, for every r theta, we're going to plug in a negative r negative theta. So there's my original, 4 over 3 minus 2 sine of theta. I'm going to plug in a negative r and a negative theta there. And when I apply my even or odd identity, I get 4 over 3 plus 2 sine theta with a negative r over here. Now the question is, when I divide through by a negative, where does the negative go? Do I put it at the top? Do I put it at the bottom? Do I put it in front? And you know from early math, you only put it in one location. And I chose to divide through the bottom part by the negative because the sign is the piece that is really making the determination whether I've got the same type of graph. So here I divided negative 1 down here, so I got negative 3 minus 2 sine of theta. So if I compare this entire graph with this entire graph, I can see here I have negative 2 sine theta, which is good. And then the only other difference is I've got this 3 and the negative 3. That's the situation where I'm going to get the exact same graph, but if I graph them, they're going to start and end in different spots. So these two graphs are identical, even though they don't look like it because of the extra minus sign right there. But since that minus sign is only on that one piece, that's just going to change the direction of the graph. So yes, I do have theta equals pi over 2 symmetry. And then finally, pole symmetry. If I just make this side a negative and then divide through by a negative, I can see I don't have the same as the original. So we can say most likely there's no pole symmetry. And once again, confirming on the calculator, the theta equals pi over 2 symmetry is the only one. The very last example, r squared equals 4 cosine of 2 theta. This one, actually all three symmetries exist. When I plug in r theta, or for every r theta, I plug in r negative theta. Cosine is an even function, so that negative sign goes away, so I end up with my original again, r squared equals 4 cosine 2 theta. So I've got polar axis symmetry. The second one, for every negative r, or for every r theta, I'm plugging in negative r negative theta. Well, negative r quantity squared is just positive r again. And once again, this minus sign inside the cosine function, since cosine is even, it goes away. So I end up with the same original. And then finally across the pole here, r squared equals 4 cosine 2 theta. If I plug in a negative r squared is r squared. So for that one, I have all three types of symmetry.